Another application of trig functions is about harmonic motions. First one is simple harmonic motion. Next one is damped harmonic motion. The other one is resonance. We use trig functions. We use cosine and sine to define these three kind of motions. Why we do that is because they are periodic. The first one, simple harmonic motion, means the kind of motion in which resistive forces like friction, air resistance is negligible. That means the amplitude stays the same, more or less the same. An example is a pendulum, the way it swings to and fro. So long as there is some energy in the system, the pendulum will swing to and fro. Another example is when you have a child in a swing and you push the child to swing, the child goes like this. So long as you maintain the same amount of energy to push the child so that the child swings, the motion is simple harmonic motion. The amplitude doesn't change over time. In the second case, amplitude stays the same. In the second harmonic motion, the damped harmonic motion, the amplitude diminishes over time. An example is when you have the child swinging, you push the child, goes up, comes back, and then if you stop supplying energy to the swinging child, the child will stop swinging to and fro. That means the amplitude dies down with time. The third one, the energy that is applied to maintain simple harmonic motion is too much. And what happens is that sometimes the energy might be too much and it might cause, like in the case of, let's say you are swinging a child to and fro and you supply too much energy, what happens is that the child will swing up and then will fall down. And that would not be good at all. So right here we say that amplitude increases over time. Of the three harmonic motions, the one that we do is simple harmonic motion. There are two equations that we use to define simple harmonic motion. And the first one is D is A cosine omega t. Next one is D is A sine omega t. Omega is angular frequency. D is the displacement. This A is the amplitude. Now from here we'll talk about the time it takes a particle to complete one oscillation. That is one period. Say period is equal to 2 pi over omega. And from here we can talk about frequency. And frequency is simply the reciprocal of period. So you can say 1 over period or omega over 2 pi. And we apply this in a few minutes. And before we go to the examples, the first one is applied if the displacement starts from the highest point. Next one, this is when the displacement starts at the equilibrium point or the rest position. The example that we have for this subsection about simple harmonic motion is right there. An object is attached to a coiled spring. It's pulled down a distance of 6 inches from its rest position or equilibrium position and released. So it's pulled. This is the diagram here. This is the spring. This is the object. It's pulled down 6 inches. It's somewhere here. So this is 6. And this is the rest position. That means this must be -6. It's pulled down here and then released. So it will start swinging up and down. So since the swinging starts at the highest point or the lowest point, we use the first equation. That is say D is A cosine omega t. So you say D, it's the displacement, is equal to A. So A happens to be the amplitude, right there, negative 6 cosine omega t. We are given that the time it takes for one complete oscillation simply means one period. One complete oscillation is period, and the formula is 2 pi over omega. And the time, that's the period right there, is 5 seconds. So this is equal to 5 seconds. So we write this over 1 and cross multiply. Say 5 omega is equal to 2 pi. To find omega, we divide by 5. So omega is 2/5 pi. And now we can write the function that models the position of the object at any time. So you say d is equal to negative 6 cosine omega. It's right there. We found it, 2 pi. That's what we wanted to get. And now we want to find the position at t is 1.2 seconds. So what do? We just substitute 1.2 for t right there. D will be negative 6 cosine 2/5 pi times 1.2. And this one will be, round this to the nearest 10th. Make sure your calculator is in radians. So this one will be to the nearest 10th will be negative 2.2. That's where the object will be when t is 1.2 seconds. We are also asked to find the frequency. We have the period, 5 seconds, 5 seconds. That means the frequency is 1/5. Just that.